Oh no. So, the last time we talked about approximate policy iteration, I guess, and we couldn't quite finish. So today I'd like to start with that and finishing up approximate policy evaluation. And after doing that, we should talk about the result, look at whether some parts of it can be improved or not. That is, we're going to look at some lower bounds, which are going to be fun, I hope. So what is this thing that we were looking at? So we wanted to scale up, and then we said that, okay, let's imagine that we have these features, we are still doing planning, but we have access to these features. And we made this very strong assumption, hoping that we will get a great result. Under a strong assumption, you should get a great result. That the action value function of all the policies lies in the span of the features, or maybe lies close to the span of the features. We'll see that. But we already relaxed it. Like we just say that, okay, we just want to get a good policy at the end if it's true that for all the policies, the value functions, action value functions lies close to the span of the features. And then what can what can we do in that case? What would be a reasonable algorithm? We ended up looking at a version of policy iteration, which would start with some policy p0, and then well, policy iteration starts with evaluating that policy. So in this case, evaluation means every time you need to evaluate a policy, because you have a huge state action space, you can't calculate all the state action values for each state action pair because there are too many of them. So we're going to take advantage of the features and these assumptions. So we're going to just calculate parameters such that the function that is obtained by linearly combining features with those parameters is close to the true action value function of that policy p0 that we started with. And of course, we're going to use a simulator to come up with these parameters theta naught. So theta naught in general is random. It's based on the simulation outcomes. And then we want to design a good procedure such that this equality can always be made to hold, but it will hold with a small error. So this error term here is just an error function, the difference between the left-hand side and the right-hand side. So epsilon naught is just q naught minus q pi naught. And we want that maybe the max norm of this error is small. And so that will be one part of the challenge. That is, if you are given a policy like pi naught, how do you find these parameters? So this is called policy evaluation. How do you find these parameters so that the error is uniformly back controlled? And then, as in policy iteration, once you have the action value function in your hands, you can greedify with respect to it. You can take the next policy, which is greedy with respect to the previous action value function that you found. In this case, the action value function is not precise, so we can't really greedify with respect to q pi naught, but we can greedify with respect to q naught, and this is what we do to get pi 1. And then the process continues in the k step. Generally, pi k is going to be greedy with respect to qk, which was the approximate value function of, oops, well, look at the typo, of the previous policy. And then after you do this for some large number of iterations, you want to stop and you want to say, this policy is maybe good enough for me. And the question is going to be, how many iterations are we going to need in total? And to keep, to arrive at a policy which is near optimal, and how precisely should we be evaluating these policies, and how much simulation effort and computation effort goes into these policy evaluation steps. And so naturally, we want the policy to be good. So we're comparing it with the optimal value function, its value function, and you want the error to be small. And the analysis is broken into two parts. One is to understand how to do policy evaluation well so that these uniform errors are well controlled. And the other is how do errors propagate in this procedure? Because you're approximately evaluating the policies. So that's the second part. And for the first part, we had this lemma that stated the following. You pick any policy in this setting, and then you can come up with a procedure which used optimal experiment design to come up with state action pairs where you're going to run the policy from for each number of steps to measure the returns and do that m times and run least squares on the so you do this m times, you average the results, and those are your targets at those state action pairs. And you're fitting with least squares to the state action pairs. It's going to be a weighted least squares fit where weighting coefficients are coming from maybe the Kiefer-Wolfowitz theorem. And then the result was that for any delta with probability 1 minus delta, the maximum error of the prediction, the maximum prediction error across all state action pairs, could be infinitely many, but okay, mostly we're just doing finite, but like it doesn't matter how many they are, is going to be controlled as follows. So the bound has three terms. The first term is just the absolute error that you get if you were given all the information about Q pi and you found the best fitting procedure to control the maximum error. So this is the minimum of the uniform error. The best possible parameter would give you this error. So this is the error floor. No one can go below this error if they're using these features. So that's the ultimate target. If we can get there, then we're happy. In the so-called realizable case, so the case that we started with, when we assume that the action value function lies in the span of the features, then this error is just zero, right? So here we're just saying, oh, it could be not zero. And then like, okay, it will be just some error there. And then you choose better features, maybe then this error is going to be smaller. And then the second term is going to be like, okay, so then that is the second kind of thing. So this is the irreducible error that no one can reduce, that just comes from the existence, like from the fact that the features are not perfect. And then there are all the other errors. And here you see this approximation error again, but multiplied by this factor of square root of d, which came from the Kiefer-Wolfowitz theorem. And at this stage, we should be positive about whether this square root of d is really necessary. We know that in the Kiefer-Wolfowitz theorem, this error is necessary, but maybe least squares is not a clever procedure. Maybe with some other procedure, you could reduce this error, right? So square root is d is there. And then there is another term, which is like all of these terms are multiplied with square root of d. So this term depends exponentially. It's exponentially decaying with increasing horizon. So the horizon was like for how long you went with simulating your policy, how many steps. So that was a truncation horizon. And so we see that if you want to keep this small, then you just have to, choose it h big. Then this error term is going to go away. And the final error term, I don't know how well you can see it. It's kind of messy. It just log 2 times the cardinality of this set at which we are doing this rollout n times, divided by data, which was our failure probability parameter, divided by the whole thing divided by 2m, and m was the number of rollouts per state action pair. Okay. And there is 1 over 1 minus gamma multiplying the whole thing. And of course, so C, lucky for us, the Kiefer-Wolf's theorem tells us that you don't have to have too many state action pairs at which you are measuring responses. So roughly d squared is enough. If you allow a factor of 2 here, then this could be brought down to almost linear. So that's great. We shouldn't worry too much about that. So log C in particular is log D. So this is a small term there. And so M has to keep up with this. That's good. Number of states appears nowhere in this right-hand side. So we can control the errors regardless of how many states they are, despite the fact that there could be many, many state action pairs. All right, so this was the first lemma that we had, which was just the consequence of the Kiefer-Wolf's theorem and the simple calculation with least squares. Right, so this is good because we see that this answers the question, can we do this policy evaluation and control all the errors that appear? Well, the best error that we can hope for is kind of like just this approximation error. But if you take h to be big enough, then maybe you can match this term to this term, and then you can, if you make m big enough, you can match this term to the approximation error as well. And you can calculate like how big this truncation horizon should be the effective horizon at the approximation level. And how big the number of rollouts should be at these core states. And it should be roughly at the effective horizon for the same approximation policy, because you have this 1 over 1 minus gamma. And it has to be squared because there was a square root, and you have to multiply the whole thing with log d, basically. So it's a tolerable number of rollouts that you can get away with in policy evaluation. So this was the result for policy evaluation. So far so good. So we can record that h should be the effective horizon matching the approximation error, and m should be maybe the same effective horizon squared times log, I don't know, 2d squared divided by that, or something like that. So that's good. That's polynomial in the relevant quantities that we want. And so the second part of the analysis is looking at that if you take any memoryless policy, pi, and you take a policy which is greedy with respect to an action value function, just a function of state action pairs, which is not necessarily the action value function of the underlying policy, but differs from it by some epsilon. Epsilon is again this function, this error function. Then the question was, is it true, and to what extent is it true that you're making progress in terms of that the action value function of the next policy would be closer to the optimal action value function than the action value function of the previous policy was. And we saw that with the usual contraction argument, we can get this result that says that, yes, the error of the new policy is at most gamma times the error of the previous policy plus 2 times the maximum uniform norm of this error term divided by 1 minus gamma. And so if you wish, you can iterate this. So calling the error of the case iterate delta k, you see that delta k plus 1 is smaller than equal to gamma delta k plus, let's call this epsilon over 1 minus gamma. And then if you plug in the same inequality for delta k, then you get this. You kind of rearrange things, and then you see that, well, you get a gamma squared compared to the iterate 2 times ago. So the minus 1 kind of matches this 2 here. And then here the terms are starting to pile up, but because of the discounting, even the infinite sum of those terms, the terms would look like 1 plus gamma squared, and so forth. They're bounded by 1 over 1 minus gamma. So there is nothing to be much worried about. And altogether, all this means is that you can bound the error of the case iterate as gamma to the power of k times the error of the first iterate plus epsilon over 1 minus gamma squared. And this can be bounded, assuming that the rewards are between 0 and 1, also by 1 over 1 minus gamma. And so if the number of iterates is large enough, then this initial error disappears. It actually disappears exponentially fast. And the error that you're going to get is just proportional to epsilon up to this 1 over minus gamma squared factor. All right. And now you can ask the question, okay, so this is all good. So we are making progress because the first result says that we can control this max norm errors. So that was this lemma. And then the second result says that as long as this max norm errors can all be controlled, controlling the error, we're controlling the errors of the iterates. We're still under control. And what remains to be seen is that, okay, if you have a not exact approximate, like a not exact action value function, optimal action value function, but an action value function that is close to the optimal action value function, and you greedify with respect to that, like what can you expect? And we have already seen this and then used it, and like it appears in the homeworks, right? So these policy error bounds. So the policy error bounds would say that if you have, a Q function, which is just function mapping state action pairs to reals, and you have a policy which is greedy with respect to this Q function, then V pi, the values that a policy achieves are almost as good as the best possible that you could get, except that there is some error, which results from Q not being the same as Q star. And so you remember that this is the error bound that we got. So putting everything together, so after k iterations, so putting it all together, so we're going to run policy iteration. for case steps, and we ask about the value function of this policy that we get, and based on all these results, we can see that, okay, this is how it goes. The value function is this big. We just have to plug in Q of K here. And then, of course, these can be upper bounded by the difference between the policy section value function plus the error what we make when we are trying to evaluate this policy. So this can be bounded by the policy evaluation lemma, right? So this lemma, if we choose age this big, m this big, then we can match all of these terms, and then all of these become the approximation error for the policy. So we have 1, 2, 3 of them, plus we have this square root, so it multiplies with square root d, and we have an extra. So from here, we see that this is smaller than equals, okay, in red. The approximation errors, and 1 plus 3 times square root d. So we can make these errors this small. And this guy can be bounded by from the progress lemma, right? So a progress lemma says that eventually the error is of this size. Okay, so for the case iteration, so this is smaller than equals to gamma k divided by 1 minus gamma. So we're gonna make this assumption that the rewards are in 0, 1. You kind of always just make this assumption whenever it's convenient. We have enough trouble even without this assumption. And then there is this epsilon. So the epsilon was the approximation error that we commit when we are doing the policy evaluation, and we just argued that those can be kept at this level. So just write the same thing, approximation error, 1 plus 3 times square root of d, and divided by 1 minus gamma squared, right? Because we had this. All right, so putting everything together. Oh, let's choose k, the number of iterations, to be the effective horizon for, I don't know, like match this term. We already have this term, so why not? So 1 minus gamma times epsilon approximation error. Then these guys have the same size. Well, okay, I put everything there. And so then the first term is upper bounded by, I don't know, 2 times approximation error 1 plus 3 square root d divided 1 minus gamma squared, plus there is this other guy, which is like without the 1 over 1 minus gamma squared, but like I'm just going to inflate it and put a 3 here. Because we are not that picky today about these constants, like we have enough trouble without controlling the, I mean, like control. The constants are fine, like they're not too big yet. So this means that, okay, so I was ignoring some little fact, and someone maybe can tell me what I was ignoring. It's related to using the policy evaluation lemma. How many times did I use this lemma in the argument? Yeah, I used it k times, right? Because I have to control the error in every iteration. There were k iterations, so I use it k times. And because of that, there is an inflation of the error. So you have to apply a union bound. And now your data has to be divided by k, which becomes this effective horizon anyway. So this h gamma at the approximation level. So this delta needs to be inflated by that. This delta here. That's a log factor, right? So we have to be careful when we write, okay, so what are we doing here? So we want to say with probability 1 minus delta, something holds. So V of pi k is at least as large as V star minus, and then maybe we want to say 3 times the approximation error times 1 plus 3 square root d divided by 1 minus gamma cube, and then there is also a factor of 2 that's creeping in here, so that becomes a 6. So either we say that, okay, like this delta has to be multiplied with this k, with this value, or m, when you choose m, you remember m was the effective horizon, something like this, squared times the log of 2d squared divided by that. And if I divide the delta here by k, like this value here, at h gamma 1 minus gamma blah 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 blah, it goes up. Into the numerator, and we see that this has a small impact of we have to inflate the number of rollouts because we have to be prepared that the bad events keep happening for every iteration. But it's not a major effect. It's just a log factor, right? And ultimately, what we see is that as a result of this, well, we can state this as a theorem. Okay, copy it here. The theorem is going to be that if I choose k as above, so it's the effective horizon, this approximation level, and I choose m, the number of rollouts as shown above, the same age. And I choose age to be, that was just, I think that's, where was it? Yes, this is it. So this is the parameter settings for the procedure, for this approximate policy evaluation procedure, least squares policy evaluation, or whatever you want to call it. So we run it for k iterations, where this approximation error is if you take all policies, and for all policies you take the best linear fit with the features of the action value function of the policy in infinity norm. So that's your approximation error. Then it holds that with probability 1 minus delta, so delta was an arbitrary number between 0 and 1, this holds. So let's copy that. The policy is good. The policy that you read out is going to be, I forgot, 6. All right. So if we start with features, where the approximation error is very, very small, then okay, like our efforts are going to scale with that. But if you remember the definition of this was like log 1 over 1 minus gamma epsilon approximation divided by 1 minus gamma or something like that. So it's like just logarithmic dependence on this approximation error. It's relatively mild. Then with these dependencies altogether, it's not too harsh amount of computation and simulation. You can read out the policy, which is epsilon good. And if you if the approximation error was 0, by the way, then you can also derive that, okay, so here we arbitrarily chose this targets so that we are matching this irreducible error with this other guys, but like you can choose any other epsilon. Like if the approximation error is 0, then like, okay, these terms go away. So that's like 1 plus square root d. So one out of the 1 plus 3 square root d, you can get rid of 1 plus square root d if the approximation error is 0. And then 2 times the epsilon that you chose remains, right? So maybe a better way of writing this is that you can choose your own epsilon. So get rid of this, get rid of this, get rid of this. And then here, instead of this, you have 1 plus square root d plus epsilon 2 epsilon square root d. So altogether, this is the error bound that you would get, right? So there is the irreducible error. Maybe that's 0, in which case you only get this error. And the total amount of number of queries and number of compute is going to be polynomial in D. We had D squared core states. It's going to be polynomial in log 1 over epsilon it's going to be polynomial in this effective horizon. And is there any other term? There is, that's it, right? Because the total amount of compute and simulation and whatnot, like you had d squared core states, for each of them you do m row loads, and you do this for k iterations, and the truncation horizon is age. So this is like you multiply everything together and you multiply with d squareds. That's your total compute, and that's your simulation effort.
Is delta hidden somewhere?
Oh yeah, like the log 1 over delta is also there.
Okay.
If you want to get the bound on the expected error and you don't want to deal with this with probability 1 minus delta, then you could just like do that by adjusting delta to be sufficiently small so that even like on the error event when you're losing something, you're not losing much. You're losing just this much by setting the delta small enough. Because the maximum value that you can lose is 1 over 1 minus gamma. So 1 over 1 minus gamma times delta, if delta is small enough so that that's smaller than this target, then altogether this is how much you lose. And so for that, you can control the expected loss of your policy as well. So that's the story, right? So we see that under this, for this algorithm, okay, if the approximation error is not too bad, then things can be under control. You can drive the errors to be as small as you want, up to some inflation of the approximation error. So the inflation is happening because of the square root of d, and this 1 over 1 minus gamma cube. So this is like a horizon effect, and this is like a functional approximation effect. And so that's the result that you can get for approximate policy iteration. Does this make sense? All right, so big caveat though, right? So things that we don't like about this result. So that C, how do we get it? Right. So it would be better to have the same result. So this assumes, like this doesn't take into account the time it takes to compute C, if you need to compute that. In the worst case, we argue that we have no good way of computing C for an arbitrary feature map without looking at basically all the state action pairs. Just an adversary argument. So it would be better to have similar result without that, but we don't have that. The other problem is that this approximation error is inflated by the square root of d, and then it's also inflated by this horizon effect. Are these necessary? So the rest doesn't bother us that much because you can control this by choosing epsilon to be small enough, and the price of that is just logarithmic. So epsilon didn't appear anywhere except for logarithmic factors. And maybe another caveat is that, okay, like if you really wanted to get this result that I was talking about first, so epsilon is matched to epsilon approximation. how do you know how small is this approximation error? You have not the faintest idea. And then you might wonder about whether it's possible to get a procedure that still achieves this result. And interestingly, well, there is this usual trick. It's called a doubling trick, that you make a guess for what would be a good value for epsilon. You say, oh, maybe 1 is good. Well, actually, if the whole range is like 1 over 1 minus gamma, you should start with the range or half of the range. And then you run your procedure, you get a policy, and then you half it. Half this parameter, run the procedure, get again a policy, and so on and so forth. And then maybe at the end, you just like check which policy is the best, and you return that. So this way, well, actually, this way, you may not be able to detect that it's time to stop, but you don't even need to check. Like, if you can have this anytime procedure, that if you have more time to run your algorithm, then it can do the best that anyone with this type of procedure would be able to do if they knew what the value of the approximation error is. So if you knew what the approximation error is and you wanted to set your budget, like set your epsilon based on some time budget that you have, like you have a set value for like how much computation you can do or how much simulation you can do, then you could try to match the epsilon to that. And if you want to match this, you don't have to do the hard calculation, because you can just do this halving procedure and it will automatically figure out everything for you, right? So the only real parameter in this algorithm is this epsilon. And if you have no idea about what epsilon to shoot for, the recommendation is that you start with a large value of epsilon, you keep halving it. The extra cost, and then like when you run out of time, you just stop and you return the policy that you obtained at the end when you were able to, like run everything up to the end. And the guarantee that you can get for this is that this is almost as good, like within a constant factor of knowing how much time it would have taken, like doing this calculation in reverse, like knowing everything. You calculate the optimal value of epsilon that would just fit into your budget, and then running the procedure. So compared to this, maybe you lose a factor of 2. So it's not big.
Can I ask a question about epsilon approximate, D, and then regular epsilon?
Yeah.
So let's say that we want to just blow up D and let it get really big, then I assume that would drive the approximation error down as you start to just like get to a tabular representation.
Feature space, yeah.
Yeah, but then you would blow up the other, is that the accuracy error, and then one's like the truncation error? Like
what? So this is controlling the truncation.
Okay. I guess the question is, like, if we let D get big, then we can maybe control epsilon approximate at a cost of the other term, because we would have to run more and more iterations to control.
I think it's highly problematic to try to do this because of the presence of the square root of D. So if you start to blow up the feature space dimension and you're not careful, then if the square root of D is a real effect, then that can take away all the advantages of reducing the approximation error. So unfortunately, there is, in a hard way, there is no free lunch here. So one can try different feature maps and then get the best of the feature maps that are possible, but that's the best that you can do in a way. Right. Okay. Right, so this is the result. So now I want to argue that this is necessary. In the sense that if you want to keep your query complexity to be polynomial in the relevant quantities, then you can't reduce this unless you have a very special feature map. So for special feature maps, okay, sure, you can reduce it, like state aggregation kind of things. That's fine. But if you have a general feature map, then this square root of d factor is real. If you try to go below this square root of d, you pay a very steep price in both query complexity and, as a result of that, computation time as well. So how does this work? So this is based on an observation and a paper of relatively new paper of Simon Du, Shamkakare, Rusung Wong, and Lin Fyong, just last year.
Is that 2019?
Well, it's, yeah, like it appeared in 19 and then was revised in 20. But so this, the easiest to understand this though is in a bandit setting. So we haven't talked about the bandit setting, but the bandit setting is just when gamma is 0. So you have a myopic agent, or like an objective that says that myopic choices are fine. So your discount factor is 0. So in that case, we can blow up the action space and create this needle in a haystack problem. So you have one state. That's your state. And you're going to have a bunch of actions, many actions. And all of these actions lead back to the state. So this is action 1, this is action 2, and this is action A, capital A actions. And A is going to be large, maybe exponentially large in dimension. I mean, we are going to try something like that. And we're going to play this needle in a haystack argument on this. So we're going to hide somewhere in this jungle of many actions a reward of 1. So for one action, like we don't know which, it's like this special action A star. The reward is going to be 1. For all the other actions, the reward is going to be 0. Now recall that the assumption that we want to make is that the features are well approximating the action value functions of all the policies. So can we choose the features in this example in such a way that this holds? So let's say, okay, so maybe so fix this epsilon. So we're fixing the epsilon, and then I'm going to modify this set. So here I'm hiding a reward which is just big enough that it's going to be critical to find it, like this. So does there exist some feature map such that this holds? So what are the action value functions in this example, q pi? So there is one state, S, and for any policy, well, it's an action value function. So you'd say that first choose action A, and then you follow the policy. Does it matter what policy you follow? Well, it doesn't matter because gamma equals 0, right? So the action value function of any policy is just the value of the reward at that state. So we just need to make sure that the reward function can be well represented by the features, right? So there's this soup where the policy is not doing nothing now. So we have to make sure that the features are such that the reward function and okay, let me try this in a more precise way. So inf over theta of I'm still going to write this lonely state, call it S naught. Okay, you know what? I'm going to suppress the state. State is gone. So this just means that the features can represent the rewards, and I'm going to drop the state from that too. So just drop the state. Like there is only one state, like why would I carry it? And I want the maximum error to be small, right? Like for every action, I have to represent the reward well. So now I need to choose this phi map, which is from the actions to RD. And the question is, okay, so if I can choose these features such that this is smaller than this desired approximation error, and I demand that the target accuracy of the algorithm, so the suboptimality of the algorithm is delta, and delta is smaller than the approximation error. Okay. Then if I choose this example, then maybe the delta is smaller than this. Then if the algorithm misses the optimal arm, like it chooses some other arm at the end, or chooses some other action, like in Bandit's actions or arms, it chooses some other action, then it cannot be data optimal, right? Like the only data optimal choice in this case is if the algorithm finds a star, right? So because like what's the value that and a choice which is not a star is going to bring? It's going to bring 0. What's the optimal value that you could get? Well, it's this epsilon error divided by 2. And so we demand that delta is smaller than this error, and we are just meeting the error guarantee. So that's not good. Maybe make this strictly smaller. So this implies that the algorithm needs to find a star. But that's like, how can an algorithm find a star? How can an algorithm, like what can an algorithm do? Well, this is the needle in haystack problem from homework 0, right? Like the algorithm can query all the actions, can get the reward for the actions that are queried. For whatever action it hasn't queried, it has no idea about whether its reward is going to be 0 or non-zero. As long as the algorithm didn't see the non-zero reward, it has no idea about whether some other action has a 0 reward or a non-zero reward. So it has to keep querying those. So we embedded the needle in a haystack problem into this this setting now. So that means that the algorithm is going to need roughly the number of actions queries. Okay. So what remains to be seen, like how big can A be? How big, how many actions can we choose such that we can satisfy with some features this approximation requirement? Okay. So here, this is over all the actions. So here, one idea is, well, we can certainly choose D, right? So the standard Euclidean basis vectors, we could choose those. And then the parameter vector would just be, like the scaled unit vector corresponding to A star. So that's a choice. That gives you D, but that's like nothing, right? Like we are hoping that this wants to be a negative reason. We want to show that somehow it's possible to choose many more actions. The question is, how many more actions can we choose? Okay. And the idea here is that in high dimensional space, if you throw at random vectors uniformly distributed on the d-dimensional sphere, then these vectors tend to be orthogonal to each other. So randomly chosen vectors on the uniform sphere tend to be orthogonal to each other until some coordinate constraint is met. So the precise statement of this is in the Johnson-Lindenstrauss lemma. which states something like, not something, yeah. It states the following thing. For every tau and integers d and k, such that the CEAL of a times log k divided by tau squared is not more than d, and d is not more than k, then there exists these vectors phi 1, phi k, which are unit vectors. So they are on the d-dimensional sphere. And not only that, well, that would be easy. It also holds that for every pairs of these vectors, the angle between them is below tau. So how can we use this? Well, so here, realize that the condition between d and k is that d can be exponentially larger than k, right? Sorry, k. Okay. Yeah, so k can go up to e to the d, right? Like, so roughly k can be like tau squared divided by 8 d in the exponent, right? So up to this many vectors can be put on the unit sphere such that they are up to, like this tau accuracy orthogonal to each other. So with this, it becomes clear what to do here. So we can choose A in our example to be just this. I guess be conservative. And okay, so maybe tau is going to be like the approximation error. And then the Jones-Linder-Strauss lemma tells us that there exists, so from the JL lemma, it follows that there exists this phi 1, phi capital A vectors on the sphere such that the inner product between any pair of different vectors is small. So why is this good? Well, we need to satisfy that the reward function, no matter what A star is, can be represented with the features. Okay, so this inequality needs to hold. So here, for the sake of specificity, I should say that, well, there are different reward functions, and then for each of them, we need to be able to satisfy this constraint. And so these reward functions are just this epsilon times, and they give you whether A is equal to A star. So it just this needle in a haystack type of thing. So choose an A star. And we're going to choose the theta based on this A star. And we're going to choose it to be equal to epsilon approx divided by 2 times the feature vector of A star. And now we want to verify that this condition C holds. So does C hold? So if you take any action A, you have to take the inner product with theta, A star, and you have to compare it to the reward. So what is this? So this is just the inner product between phi A and phi A star. And now there are two cases. Either A is going to be A star. If A is A star, then here, because these vectors lie on a unit sphere, we just get 1. And if A is equal to A star, then the reward was chosen to be exactly the approximation error over 2. Okay, so when A is equal to A star, then this difference is just 0. And when A is not equal to A star, then we know by the choice of these vectors, right, like this choice, that their inner product is smaller than equal to this approximation error. So you get this approximation error squared over 2 minus, and here the reward has to be 0. And so we wanted to verify whether what choice satisfies that the errors are smaller than the approximation error everywhere. And so if A is equal to A star, then the error is in fact 0. And otherwise, it's the error squared divided by 2, which is smaller than the error, because the errors are smaller than. So we assume that this question is only interesting if the errors are small anyways. So from this, it follows that C does hold. Indeed. So this means that we can choose A this big, So it follows that for every algorithm, that claims that its delta sound, so delta suboptimal, returns a policy that is delta suboptimal with delta smaller than the approximation error divided by 2. There exists some feature map There exists a feature map. Okay, so D was fixed. So the feature map is assigning features to every action, where the number of actions is going to be exponential with some universal constant times approximation error squared times D. And it holds that A makes at least 8 queries. Could be A over 2 or something. So, oops. Omega A queries, which depends exponentially on the dimension, right? So if you're demanding that the suboptimality is smaller than the approximation error, you avoid the blow-up factor of square root of D, then you're going to make exponentially many queries. You can actually refine this so that at the end you get the result where this A is exponential in the ratio of the approximation error and your suboptimality level times squared times D. Which shows exactly that if delta is relatively big, then you can cancel out this D with your delta. But if delta is small compared to your epsilon, then it doesn't cancel it. And there are some bad examples where the algorithm needs to keep searching. So there are no algorithms that avoid an exponential query complexity in the dimension if we allow approximate action value functions for all policies. Even for all policies, we demand that there is some approximation error, but the target accuracy level of the procedure is smaller than square root D times the approximation error. If the target accuracy would be bigger, then there is no problem. That is the essence of this policy evaluation or like policy iteration result. It shows that you can get polynomial query and computational complexity if your target accuracy is not too high. If your target accuracy starts to be too high, then no algorithm could do that. So the way the exponential blow-up is avoided here is that we only claim that this is the target accuracy that we will ever reach, which has the square root D blow-up. of the approximation error. If we didn't include the square root of d, then the lower bound shows that no algorithm can get away with polynomial query and computation complexity. So that's kind of like a big reality check for anyone hoping that function approximation, let's say linear function approximation, can do miracles. Well, it can do miracles up to some degree, right? So if the approximation error blow up is not allowed, the square root of the blow up, then even under the most favorable conditions, no algorithm can avoid exponential query complexity. This is a very, very favorable condition that we demanded that the features are so good that they can represent all the action value functions for all the policies. Like that's a very friendly assumption. Even under that friendly assumption, algorithms which are demanded to have very high accuracy in this unrealizable setting have to suffer exponential query complexity. So no compressed calculation is possible beyond this limit unless you start to make assumptions, further assumptions about a feature map or something else, right? Like here, the feature map was chosen in an adversarial fashion, right? At the end, in the lower bound, we constructed the feature map in such a way that it gives you no information about the things that you haven't tried. This orthogonality thing was that caused this, the near orthogonality condition. Right. So why did we set the I think that here, so there was a question, why did we set the reward to the approximation level divided by 2? Well, I don't know. I think that if you demand delta suboptimality, then you should probably set this to delta, and then delta is smaller than the approximation error, and then like just modify the argument everywhere. That's a better choice. When I started talking about this, I didn't make up my mind about whether I want just to talk about that. The target accuracy should be epsilon over 2, or should it be arbitrary? Like if it's an arbitrary accuracy, then you just set this reward to data, so that it's important for any algorithm that claims data accuracy to find this reward that's sticking out by a data. Okay. And then you just scale everything appropriately. All right. So you might ask a question, does this generalize to reinforcement learning? I mean, like, yeah, this is reinforcement learning, right? So gamma equals 0. But like, okay, does it work for positive gamma? I think it does. I can't recall anyone writing this down. So I don't know. But what was in the paper is the fixed horizon setting. So the fixed horizon setting is when you have an H as a problem with exactly H stages. So the number of steps in an episode is H, capital H. And there the result is that the compute time is going to be something like the minimum of a to the h, and then this quantity that we have seen with this C universal constant. And the construction of this is not too hard. It's based on constructing an ARE tree, deterministic dynamics, the usual lower bound that we have seen previously applied to local planning. So you do the same tree construction, you hide, so the depth of the tree is chosen to be age. Well, if this is the smaller quantity, then you set the depth to age. And if this is a bigger quantity than this, then you solve the equation that this is equal to 8 to the power of h hat, and then you set the depth to h hat, because then you construct this ARE tree with deterministic dynamics. You hide the reward of 1, well, or scale it. You hide the reward of delta. It's undiscounted. So this reward propagates up in the tree at every level of the tree. All the states have a value of 0 except the state that is on the path to this leaf, which has a value of delta. And then similarly, you can reason about the action values. An action value for a policy is going to be for if the state where we're talking about the action value is not on the path to the special leaf node, then the action value from there is going to be 0. If it's there, if it chooses the right action, then the action value is going to be between 0 and delta. It could be less because the policy may decide not to go with the optimal path, right? So for every policy, we want to understand how the action value functions are, because we need to satisfy this requirement that for all policies, the action value functions are uniformly well represented. But these action value functions are basically the same needle in a haystack type of functions, and the same construction that we talked about using the Jones-only Nash-Strauss lemma at all levels of this tree is going to work with the same parameter vector choices. And so that means that now the feature space is blown up. Well, actually, in an H step problem, it's okay to have like separate parameter vectors in every stage, because this is kind of like a non-stationary problem. The number of time steps until the end of the problem does matter. So the value function depends on where you are in a stage. So the stage index is kind of part of the state, if you wish. And so now you have H parameters. So each level, you can just choose the Jones-only Nash-Strauss feature vectors and the corresponding parameter choice. And it works out beautifully and gives you this result. All right, so this, again, gives us some hard limit of what you can do in the normalizable setting. All right, I should stop here. I think this is a good place to start. So you might ask how to prove the Jones-only Nash-Strauss lemma. Well, there is a basic inequality for uniformly distributed random vectors and a sphere. So that inequality says that if U is uniformly distributed on the sphere, then the probability that the first index of this vector exceeds some beta over d is smaller than the exponential function of negative beta over 4, at least if beta is, I think, bigger than or equal to 6. So this is a basic result just for this very special distribution. And then Johnson-Lindenstrauss lemma, the proof of this uses the probabilistic method. So it's a very, very nice argument. If you want to prove that something exists, you can take a distribution of things. Like here, you want to prove that there are k vectors such and such. So then you choose k random vectors, and then you choose that the condition that you wanted the k vectors to meet is met with positive probability. And it's true that there must exist k vectors for which this condition is met. And so you just choose this vectors phi1, phi k to be uniformly random on the sphere. And then you argue by symmetry that, well, they have a unit vector, unit norm, that's fine. And then you have to argue about the inner product. Without loss of trinity, it's enough to argue about the inner product between phi1 and phi2, let's say. And then you want to argue that all of these are going to be small. Well, to argue that all of these are going to be small is the same as saying that the chance that the maximum of these are going to be large is smaller than 1. So, yeah. So it would be enough to show this, because from this it follows that with positive probability, the maximum is smaller than tau. And now to show this, you can just use a unum bound. So what's the probability that all of them are greater than tau? Well, that probability can be upper bounded by the sum of the individual probabilities, and then there are d times d minus 1 over 2 of these guys. And then there is symmetry. And then you can use that. You can, without loss of trinity, assume that phi1 is just the first standard Euclidean basis vector, and then phi2. So that this inner product will just pick the first coordinate of phi2 then, and then you just square, and then you're using this inequality and just show that this is smaller than 1, which will be true. So it's just a little calculation after we have the tail inequality. Right. I'm really using too much time.
Just a quick
Right.
question.
Any questions?
Yeah, so this result is for this particular, this is for the worst case scenario, right?
Yeah, this is a worst case for the feature maps as well, right? Like the result just says that for every algorithm, there will be a feature map on which that algorithm has to make a lot of queries. It doesn't mean that like you choose your favorite feature map, then on that feature map, it will have to have a lot of queries. There are some feature maps which are more benign from the perspective of this blow up than other feature maps. But if you want your algorithm to be agnostic to the choice of the feature map, then you immediately face this hurdle, right? And then, so here the game is really that like we don't want to express any preferences ideally for the choice of the feature maps. The feature map choice should be, you know, like the an issue that someone else is dealing with. It's not our problem. It's someone else's problem. But if they happen to choose a feature map which is very inconvenient for us, like, okay, then we have to know what to do. So that's why it's also this core set calculation is a question of like, okay, someone else chooses the feature map. How do you do this? Well, maybe one lesson from all of this is that trying to break up the problem into these different parts where someone else chooses the feature map is maybe not the brightest idea. But maybe, wow. If you demand that your algorithm should be capable of dealing with any feature map, then this blow up is just fact of life. And it also shows, like, this argument also shows that least squares wasn't that bad, by the way, right? Like, you could have suspected that least squares is losing something here because it's not tuned for, you know, the L infinity error or whatnot. But no, it didn't happen. This lower bound was independent of what algorithm you want to run. So least squares is as good as anything else in terms of this blow-up factor. Which doesn't necessarily mean that least squares is the best that you can do for every feature map, by the way. So Reach, for example, likes tie coding. And so I like to challenge everyone to think about, like, what's the blow-up factor for tie coding? Maybe it's much smaller. Maybe that's why it's a great idea. But you don't know. I think it would be worthwhile to go after that.
So when you mean the blow factor for tile coding, do you imply like to go through the Du, Kakade, Yang, and Wang lower bound proof, but maybe with this type of feature mapping as opposed to the usual like least squares linear feature mapping?
Yeah, I mean, like, yeah, we have no idea about, well, obviously the same lower bound proof doesn't work in that case because tie coding, you know, has special features, specially constructed. There are various versions, like randomly choose here and there. Like, you have to be a little bit more specific about, like, but you can imagine that you are completely specifying how you randomly tile the space, and then you ask the question, okay, if I do this, what's the worst case blow-up factor? How does it depend on the parameters that describe my feature map? So I guess one big lesson is that in reinforcement learning, okay, so the other lesson is that we kind of made it up by proving the result for approximate policy iteration that we need to control the L infinity errors. Well, yeah, in that case, everything works out, but was that really necessary? Well, now you see that, well, in a way, you're not losing anything by insisting on controlling the infinity errors, because every algorithm is going to suffer this blow-up factor of square root of d. And the blow-up factor of square root of d was coming from the demand of trying to control the infinity errors. So like that was sort of the price to pay. And it seems every algorithm is paying that price anyway. So it's like, okay, what's the big deal? So it seems that the idea that we should aim for controlling the worst case, the uniform error, was ad hoc at the beginning, but at the end we find that it's not completely ridiculous, or it's actually well founded. Because no other algorithm that tries to avoid to do this will save anything substantial. So you can't really be too clever, much more clever than approximate policy iteration. We don't know, by the way, whether, like the 1/1 minus gamma cube has to be there, or it can be reduced substantially. So that's an open question. We have similar settings where the horizon dependence is a little bit different, a little bit better. So we suspect that some or like people in the community who care about this suspect that it's possible to reduce it a little bit by being more clever about the proof, the construction. But would it change substantially the algorithm? No, it won't. So for this setting, the only remaining problem is this core set business. That at least in this setting, we shouldn't demand the algorithm to be given this set of states, state action pairs.
If I remember, I think, were you and Roshan thinking about how to relax that assumption that you're given the core states? I remember, okay, there was like something to do with solving an LP or the geometry of such.
Right, yeah, but we don't yet have an answer. But maybe there is some chance that this can actually be avoided.
You mean like in terms of trying to approximate the core states, or just not even having?
No. It's just the algorithm wouldn't need to. I mean, like, the natural thing would be to assume that you have this simulator, and you can ask the simulator for features of next states and the features of the current state, and you can reset the simulator state to a state that you have seen before. That's it. That would be the natural assumption, and no further assumptions about accessing the features for any other states. So if you're doing this local exploration with the simulator, that's what you see, and you have no other idea about the feature maps. That's like the most appealing version of the problem, and also the closest stuff like how simulators actually work.
Okay, so ideally, you'd let your algorithm run, you take a branch and then you at some point cut off the branch, reset, get the feature to the next state, and that's like, should it matter how long you run like a branch for, or ideally it wouldn't? Like if
so somehow the algorithm would need to discover for its own sake everything. Like in a way, you want to say that like the state action pairs that you're not meeting in while you're running your simulation do not matter.
Okay.
But we don't really have a solid argument yet. In a related setting that I'm going to talk about next, we do have a solid argument for that.
What setting is that?
But sometimes that happens to be true. So that's like the V-star approximation business.
Oh.
The optimal way functionalizing the span of the features. All right.
I just had a quick comment. So in this, the worst case, like, is this a coincidence that the feature vectors that are chosen using the Johnson-Lindenstrauss lemma, they are such that finding an optimal design is so easy that you can just pick any D vectors basically, and you get an optimal design. Right? Like it almost seems like I don't know if this is true, but the hard problems are also the ones where the optimal design vectors are easy to find. Is that?
That's a curious observation.
What do you mean by problem?
Sorry, Alex.
What do you mean by like a hard problem?
So this problem that you've constructed with this tree and the Johnson-Lindenstrauss lemma, that's sort of the hard instance, right? So it still satisfies the feature requirements, but it is somehow hard, right? Informationally hard. But one property of this sort of feature vectors is that if you just pick any D vectors, then since they're all mutually orthogonal, you have basically found a close to optimal design, right? So, and we were arguing before that it might be hard in general to come up with a close to optimal design, because how do you find this set of vectors that nicely spans the feature space, right? So I don't know if it is true that there's something going on there, but at least for this hard example, it so happens that finding the optimal design vectors is also easy. But I don't know if
there is some relationship between the two, but I'm not sure.
Yeah, so somehow it seems like finding the optimal design vectors is hard if there are some interesting structure in the feature vectors, like if they happen to somehow not be totally independent. But then that is also where you can make maximum use of the feature vectors, right, to generalize.
Yeah. So like if there is dependency in the feature vectors, then finding the optimal design will take more time because you have to avoid the dependencies, right? So because those are not helping you with the design.
Right.
But if there are dependencies between the feature vectors, that helps you with generalization. And here, the informationally hard case is when the features don't help you with generalization. So intuitively speaking, it seems that what you're saying is right. I wouldn't know how to phrase it as a crisp mathematical result yet, but it seems that there is something there.
Right.
Yeah, good point.
Yeah, and ultimately, if we actually solve this problem and find matching and upper and lower bounds, then presumably we will be able to answer that better, like what's going on there.
Yeah.
I guess then like a follow-up is, why would we care about these hard problems if generalization doesn't help? Don't we mainly care about problems where generalization would help?
Yeah.
Solving problems that, we're saying, oh, these hard problems can't be solved because they're hard. And then it's like, just run a tabular algorithm and or just don't do it. I'll try something else.
I mean, yeah, like if there is a problem instance that no algorithm can do well on the problem instance, usually we don't care about it because, well, okay, no algorithm can do anything about it. So why would we focus our efforts on worrying about something that is not under control? Like we should worry about the cases where things are under control. Just the fact that we brought in the feature maps is exactly already because of that. Because things in general without feature maps are out of control, right? Like you can hide these needles in a haystack. You have to look at all state action paths. That's kind of like hopeless. You already bring in the feature map, but now it turns out that, well, okay, some feature maps are worse than the others, right? So it's just like refining the thinking that there could be things which are not under control, and don't worry about those. And keep pushing the limits for the case where you have a chance of making a difference.
I guess, then it would make sense that for problems where you have interesting structures, it would be hard to choose a good feature map because maybe that's the new needle in the haystack problem. Find like the unique feature map that
I don't believe that. I think that there is a lot of redundancy in the world. And choosing the feature map is about factoring out the redundancies. So, and a lot of problems which are, practically significant, interesting, do have a lot of redundancies. And we can be clever about those.
Right. So maybe the sort of the hand-wavy lesson is there is more to the quality of, like, this Johnson-Linden-Strauss construction is telling us that you can construct a good feature map by the definition of good here, which nevertheless is not very helpful. And so somehow we need like a better definition of what a good feature map is, rather than just saying that the value functions are well representable or whatever.
Sure. I mean, like, there is alternates to this assumption, but yeah, I guess I would be also inclined to say that this assumption that all action value functions are well represented is already very optimistic. And in a way restrictive, and you wish to relax it, but already under this restrictive assumption, it seems that things can go really bad. That's kind of interesting. So it's hard to say whether you should change these. I guess, like, you want to see under various assumptions what's possible, what's not possible, and then see the strengths and the weaknesses of the choices of the assumptions, the implications in terms of what algorithm you should be using under the assumptions, and vice versa, right? Like, for every algorithm, maybe there is some assumptions under which they work better, and then you can compare algorithms based on comparing the assumptions under which they work well. And if you find that, okay, like, some works better on more general assumptions and a broader set of conditions, then that's a superior algorithm than the other. Most likely what you're going to find is that nothing is comparable to each other, which is also information, right? Then we know that, okay, like, if you want approximate value iteration or approximate policy iteration, there are situations when one is good, the other is bad, and vice versa.
Yeah, and I guess the fact that we are now quibbling about a root D is itself it's not a bad thing. It's like, sure, we can talk about whether or not you want to get rid of that, but we already made like a significant. Yeah, so I guess it's wrong to say that this is a bad definition of a good feature map, because it does let us get to at least a root D. Right? So
yeah, exactly. It's just a definition, and then we see the corollaries of this definition, and that's good information.
Yeah.
I guess.
Yeah.
I guess then, if we're talking about the restrictive assumptions of like realizability, should we think more about misspecification than we currently do? Like, maybe make that kind of the default model?
This is misspecification, right?
Yeah.
Yeah. So this is misspecification in the context of an otherwise very strong assumption, or an assumption that people think is very strong. And then you must be wondering about, like, okay, how bad things can be if you are trying to make a milder assumption that will apply to a broader class of MDPs. And that's what we're going to talk about next.
A broader class, do you mean like, like a generalization of like a linear MDP, or?
But the linear MDP assumption is an even stronger assumption than this, right? Like in linear MDPs, the action wave functions are linear.
Oh,
So
maybe I meant,
it's even stronger. That's a closeness assumption.
maybe I meant like stronger, like more general as in to more general function approximation schemes, or more general as in, I guess I was ask, maybe I was. What do you mean by more general class of MDPs?
Bigger class.
Okay.
So larger class.
But like larger because we're using more, like we're
So
broadening.
this does only apply to MDPs for which this assumption is met, right?
Oh, okay.
For any given epsilon, this rows out a bunch of MDPs. You get like, remember the picture that I drew, like a big fat set of MDPs and then the very thin set that you're talking about. This is what's happening here. We're talking about this very thin set, and the very thin set we are still kind of struggling a little bit.
But this is under linear function approximation, where we're going to kind of loosen the closeness assumptions.
Right. Yeah. Okay. Good. Any other questions?
There might be more after the next class, but
Okay. Good.